joint work with Oded, Schramm, and Wendell and Werner. I want to talk about the problem of the self-avoiding walk, which is still a very big open problem from a mathematical perspective. What I'd like to do is discuss the planar self-avoiding walk, make some conjectures, which is basically making a precise version of conjectures that exist in the physics literature about what conformal invariance means. Then I will assume conformal invariance and actually prove a theorem which will tell us things about the self-avoiding walk. In particular, we'll be able to figure out, say, what the critical exponents are, assuming the conjectures are correct. I will actually have no theorems per se about self-avoiding walk. It would only be conjecturing and is given a conjectural limit. For definitions, self-avoiding walk, for my purpose, is just a sequence of lattice points in Z2, each distance 1 from each other and with no self-intersections. And my self-avoiding walks can begin and end at any point. I'm not right now. So I can, just for notation, let lambda n x y be the set of self-avoiding walks of length n starting at x, ending at y. That's some set. Gamma nx are those of length n starting at x with any ending point. Lambda n is just all walks of length n. And so I don't have to write lambda n of 0. I'll write lambda n star for lambda n is 0. So that's a set of self-avoiding walks of length n starting at the origin. And if I don't have a subscript n, like in lambda, then that's self-avoiding walks of all possible finite lengths, just the union of all walks. It's well known there's a connective constant defined by saying that the number of self-avoiding walks starting at the origin of length n is approximately beta to the n in this. And this beta is a number with having to do with the square lattice. And it's, I also don't know the best value. I've been in 2.6 something or other. But there's probably, it's not an interesting number. It's particular to the square lattice, and it's not what we're particularly interested in today. What we're interested in are the critical exponents, which are expected to be universal, whether we do a square lattice, hexagonal lattice, whatever kind of lattice we use. And many people have seen these things. Let me just review them real quickly. There's nu, which can be said just roughly is that the average diameter of an omega chosen of length n is about n to the nu. There's the exponent gamma, number of walks of length n, starting at the origin, is about beta to the n. Then it's the correction term here. And gamma is the standard terminology used in the physics literature, so I use it even though it's a gamma minus 1 that appears there. Or as Fendelin said in his talk, I think there's another way of looking at it is that if I take two self-avoiding walks of length n chosen from the uniform distribution, I can ask whether I can take these two self-avoiding walks, put them together, and make a walk of length 2n, and that decays like n to the minus that exponent. And there's one other exponent that I'm not sure what the standard letter is, so I just made up a letter. I'm calling it rho. And think of it as the probability that a self-avoiding walk, and this should be in lambda n star. If I have a self-avoiding walk of length n starting at the origin, there's some probability that it stays in the upper half plane. And I'm just calling that exponent rho, so it looks like n to the minus rho. And there have been predictions for these exponents, Nienhuis and Flory. I'm intentionally not giving the values of them because our goal is to actually show how you can conclude these just from making some assumptions and some theorems. So right now we just think of them as being some.
The rho was done by John Carty.
Oh, rho was done by John Carty? Okay, thank you. Well, but the basic conjecture is that at criticality, the continuum limit of self-avoiding walks is conformally invariant. And the first thing I want to do is make a precise statement of this conjecture so that people know exactly what I mean by it. And what I'm going to call conformally invariant, some might call conformally covariant. I'll tell you about that in a second. So first, the notion of criticality. Criticality means that the critical temperature, or the critical value of the parameter, Basically, that means for every walk of length n, we're going to give weight beta to the minus n. So that's the measures. And just mathematically, we're just going to let mu be the measure on all self-avoiding walks that happens to give measure beta to the minus n to a walk of length n. That's just notation. That's criticality. So that's one of the words. Second is continuum limit. I'm going to do two versions, a chordal version and a radial version. We'll start with the chordal version. Suppose I have a domain in C, R2 or C, and suppose I have 2 points on the boundary. Let's assume that the boundary is smooth right now. And let's assume for ease that the boundary points are lattice points. Then I'll put a lattice spacing of small size, say 1 over n, lattice size 1 over n there. And I look at the walk starting at Z, ending at W, or vice versa, that stay in the domain. So that's just some collection of the self-avoiding walks. And so that collection of self-avoiding walks has some mu measure. And we're going to assume the existence of an exponent, I just call it A, such that as n goes to infinity, this measure looks like a constant times n to the minus a. Basically, this a is just a simple function of nu, gamma, and rho under the assumptions. If you're going to guess what it's going to be, it's just a function of the three simple function of those exponents. So to scale, we'll multiply the measure by an n to the a, and then we get a limit. This constant here, c sub d, zw, does depend on the particular domain z and w. The assumption is that the n to the minus a will work for all domains and all z and w, at least if you're sufficiently smooth on the boundary, but the constant factor will depend on the domain z and w. Having said that, we can make a conjecture as to what a continuum limit is. We conjecture as n goes to infinity, these measures converge to some measure on paths connecting w and z in D. For our purposes, I'm not worried about the parameterization of paths. And for today, I'm going to assume that the limit is actually on simple paths. That's believed to be true for self-avoiding walks. So we have some measure on simple paths connecting z and w. And it's a measure which is finite, positive. Its total mass is this number, CD, ZW. And one scaling law that you can get from this is if I blow up the domain by 2D, I can put the 2D lattice in, I can see what happens. There's got to be a scaling law where this A comes out in the scaling. So here, this just means the total mass of the measure. So this is like a scaling dimension, I guess, in the physics literature. So that's what we mean by the continuum limit. I just want to say one property that assuming the limit exists, it'll satisfy a certain condition called the restriction property. And let me show you the restriction property. Suppose I have a domain D, and a subdomain D prime. And for ease, let's assume that the boundaries of the two look the same at Z and W. We can worry about that. So I have the measure of paths from Z to W and D prime, the measure of paths from C to W and D. And the measure of the paths from Z to W and D prime is exactly the measure on the larger domain restricted to the D prime. That just follows just from the limit. But that's an important property of measures. On the continuum, I will talk about it. We call that property the restriction property. So that's continuum limit. And finally, conformal invariance. We assume that, suppose I have a domain D, and I have a conformal transformation of D onto D prime, sending Z to F of Z and W to F of W. Then the assumption is that this measure on paths is conformally invariant, except for a scaling factor that has to be there. If we can just see from the multiplication by 2 or something that there has to be a scaling factor. And in fact, the scaling factor will be of this form. This is similar to assumptions made in the physics literature. In the physics literature, there tend to be assumptions about conformal fields in the limit. Some of us who are challenged by such things are challenged by things that aren't well defined in terms of conformal fields. In this case, we're talking about a measure on paths, which is a well-defined mathematical object. I also am just making the assumption of conformal invariance. I'm not proving it, but at least I'm making a precise statement.
You measure on paths is really what we call the correlation function of the 2 points omega z.
That's not the correlation function. It's something. Now, the correlation function you can get from the paths, but not the.
You have put the weight. Exactly
what? Well, maybe if you know all correlation functions, you might have. Okay.
What you're talking about is the integral of this measure, and what we are discussing is the probability distribution of the process. But you would have to fix a few interior points.
Okay. There's another property this measure has, which is, suppose we took the measure from z to w, and suppose we made it a probability measure. So we don't worry about the constant factor. And suppose in this probability measure, you were given part of the curve. So you were given this part of the curve, and you haven't seen the rest of it. And you want to know what's the distribution of the rest of it given this. Well, the construction also tells you, assuming conformal invariance, that the rest of it should be just what you would get if you had used this domain and gone from that point to that point. And for those who are here this morning, that's very reminiscent of the kind of things that were done for SLE processes. The domain would be the domain with gamma removed. So I assume I've seen gamma so far, and I want to continue gamma. I remove gamma from the domain, and there's my special point, z prime or something. And I continue from there.
Except that your boundaries of your domains might have had to be smooth so that your curve gamma.
We aren't worrying about that. That's not a problem. That's only a problem in the normalization of the measure. So we're normalizing all the measures to be 1 at this point. So I can normalize by infinity. Don't worry. It's normalized to be 1. I mean, you can make a big rigorous statement of that. So let me just make the same sort of statements in the radial case. In the radial case, I'm going to have a w and a z. In this case, a w on the inside, a z on the outside of the domain. Again, I have this very small lattice inside, and I look at all walks from w to z. And the measure of such things will scale by some n to the minus b, again, which would be the function of those 3 critical exponents, assuming the world is good, times some factor cd zw. And again, we're going to assume, as n goes to infinity, the measures converge to some measure on simple paths starting from w to z. And I'm going to go very quickly because these are very analogous pictures. Again, this measure would satisfy restriction property. If I had a smaller domain d prime, and I looked at the measure from w to z, it's begotten by just taking the measure in the larger domain and restricting to those paths that stay between d prime and z. Yeah.
Since you begin with this restriction property again, I'm trying to understand. Have you really defined how to restrict the walk? Or it seems you say it's a property, so...
if the limit exists, if I assume that limit on the discrete level exists, it satisfies it on the discrete level. It's just an obvious thing that's satisfying the discrete level, and therefore would exist in the limit. Just restrict the measure. Oh, yeah, I'm not restricting the walk, just the measure to the set. In other words, the measure on d prime is exactly the measure on d restricted to those walks that stay in d prime. Because right now I defined a measure on domains with 2 points in them. So I have one measure on d in 2 points and one measure on d prime in 2 points. And all I'm saying is the measure on d prime in 2 points is the same as the measure on d with the same 2 points, restricted to those paths that stay in d prime.
But what else have you now said then that this is in the definition of the mathematician agree about this thing?
This is the discrete thing that we took the limit of has this property, so the limit will have this property.
And it has so obviously a property that I don't even see the property.
Right. So it doesn't look like an important property, but it's a very important property. The loop race walk doesn't have it, and it's actually it's why these are central charge zero systems. Let me throw us. Try to reuse that language. Again, we're okay. Yeah, I mean it's obvious. Okay, just keep it as obvious for you.
The point is this is about the measures and the limit which are candidates for limits of self-limit. It's not a discussion about self-limit, about measures on the limit.
And again, we're going to assume conformal invariance. If I take a conformal transformation, mapping z to f of z and w to f of w, I'm going to assume that the measure maps is invariant except for a correction term. And again, the correction term, turns out that the correction term, you can see the only possible correction term that makes sense is given by the derivatives at the endpoints. But there's no reason why the derivative at a boundary point should be the same as the derivative at an interior point. So I'm just calling it s and b minus s. And again, very quickly, I'll just put, this also would have the Markovian SLE property, but now it would be like a radial SLE. So now we have the properties that the limit should satisfy, and now we'll go for a theorem. The only family of measures on simple curves connecting boundary points z and w on the simply connected domain satisfying conformal invariance, or maybe I should say conformal covariance, depending on your terminology, i.e. there's an alpha such that it's conformally invariant except for a f prime alpha term. And it satisfies the restriction property. Now, if I talk about a family of measures, they would not necessarily say this, but I'm assuming this as an assumption. Right now, I'm going to assume this is an assumption, though in some sense I really don't need to. But I'll say that if I normalize it, it should be an SLE. So if you want to have these three conditions, there is only one choice. It's kappa equals 8/3 and alpha equals 5/8. There's no other possible limiting measure that has these properties. In fact, and here's a 97% theorem that we don't have quite the complete. This condition is probably not needed. In other words, this, and simple curves should be sufficient. This is nice because it tells us where to look to find one. In fact, it turns out it's kappa equals 8/3, a equals 5/8.
So what goes wrong with any other value of kappa?
The restriction.
The restriction property doesn't hold. If you well, it depends. If you assume restriction, you no longer get simple curves. If you assume SLE, you don't have restriction property. And I put three conditions. It depends which condition you want to get rid of. I'll actually get to that. The SLE so there's a theory about SLE involved in here.
But from this, I would conclude that the self-avoiding walk would be not just like percolation, it's a very special case.
It is. In other words, self-avoiding walk is a special case. That's actually, or if we assume conformal invariance, it's a very special case, therefore we know what it has to be. That's kind of the lesson. Maybe it's not conformally invariant. Maybe that assumption is wrong. Maybe the limit doesn't exist. But if it...
Because it's also saying that lots of other objects constructed microscopically, in fact, fall into the same universality concept as the self-avoiding.
Right. For instance, percolation and boundaries of Brownian motion. Right.
Why does it say that?
conformal invariance and restriction is very, very strong. So, and again, in the interior, there's only one measure. Now I'm allowing two different exponents. But even if I allow two different exponents, there's only one possible value for this. And that's kappa equals 8/3, alpha equals 5/8. Turns out alpha prime is 5/48. That's what the scaling exponents are. It's the only possibility. There's a universality in this theorem, which is not so difficult. Probably the hardest part of the theorem is a theorem about SLE, which I want to describe. It has to do with the restriction property for SLE. I'll do the chordal case. And right now, let me restrict the kappa less than 4, which is the values, well, with a simple path. I'm not worried about kappa equals 4. That's too difficult for me. So let's look at, so assume we have an SLE starting at 0 going to infinity. And suppose I have a little set A here. And I kind of want to look at SLE that's not going to hit that set. Well, I can either take I can look at SLE conditioned not to hit that set. Or instead, I could take this set A, map it by phi down here, and then do an SLE here. Now, the SLE with kappa less than 4 won't hit this set. And the question is the conditional measure here, given that you avoid A, the same as the measure over here? And when we say if that holds, we say the chordal restriction property holds for SLE. And the theorem is the chordal restriction property holds for kappa equals 8/3 and for no other kappa less than or equal to 4. And in this case, you could even say what the probability of hitting the set A is. It's actually given by phi prime 0 to the 5/8 power. And there's the 5/8 coming out. I actually like to think of this as phi prime 0 to the 5/8, phi prime infinity to the 5/8. Just over here, I just happen to choose the phi prime, the value of the particular one which had phi prime of infinity equals 1. But there's a hidden phi prime of infinity equals to the 5/8 in this formula.
Can you give us some idea why that is the only SLE?
It's in the same order of magnitude as why is SLE 6 the only one with locality. And I don't think I have time in the amount of, so I don't think I actually have time for that in this lecture. Which means it's
Is 8/3 the dual kappa to 6?
yes. Yes. Kappa equals 6 satisfies a stronger property called locality, which is why it's the model for percolation. There is a restriction property for kappa equals 6, although not in the form I gave it here, because I had to reformulate it. In some of our earlier work, we tended to use restriction and locality synonymously. We want to stop doing that. Locality and restriction are two different things, because there's this notion of restriction, which holds for 8/3, but the strong notion of locality does not hold for kappa equals 8/3. Now, you could also talk about the conformally invariant measures satisfying the restriction with other powers. For instance, if I want the power 1 in the chordal, then it's just a Brownian excursion measure. One could prove by universality that, in fact, there's only one measure on curves for each possible alpha. And one way you can do it is to take, or I shouldn't say on curves, on the hulls produced by curves, the inside hulls. And one of the corollaries is that one way I could get, there's only one which has phi prime 0 to the 5. One way I can get phi prime 0 to the 5 is to take 8 independent SLE 8/3 paths, let them all run, and take the hull generated by them. Because 8 times 5/8 is 5. Or I could take 5 independent Brownian excursions starting at 0 to infinity. That's basically a Brownian motion condition to stay in the upper half plane. I could take 5 of them. This says that the hull by 8 independent SLE 8/3 is the same as 5 Brownian motions. In particular, since the boundaries of these things tend to look alike, this partially starts showing the fact that the boundary of a Brownian motion is given by an SLE 8/3, which is part of the duality. Or another way you can say it is 1 self-avoiding walk equals 5/8 Brownian motions. There's a similar rate, since I'm running out of time, I want to skip to the final thing.
Is this theorem conditioned on your conjectures, or
This is a theorem about the continuous objects. This is a conjecture. We have self-avoiding walk. We conjectured self-avoiding walk has a certain conformal invariant limit with certain properties. We do have theorems about the conformally invariant continuum systems with those properties. We don't have theorems that say self-avoiding walk and the limit equals this. So anytime if I put self-avoiding walk, that's not a theorem. There's a similar radial restriction property. Again, it only holds for cap equals 8/3. And I'm skipping a slide here. But when you get the scaling exponent, you get a boundary 5/8. This is on the disk. So in this case, 1 is on the boundary of the disk. 0 is in the interior of the disk. And you get a 5/8, and you get a 5/48 for the interior. I'm about out of time, so I don't want to do the arithmetic. But just to summarize, if the self-avoiding walk limit exists and satisfies conformal invariance, it should satisfy restriction. That really follows from the limit in conformal invariance. And sort of Markovian SLE also kind of satisfies that. So it's basically exists and satisfies conformal invariance are the big question marks. Then the limit must be SLE 8/3. So in other words, SLE 8/3 is the continuum polymer measure. That's what should be the polymer measure, if polymer measure is defined to be the limit of self-avoiding walks. The exponents nu, gamma, and rho. Well, nu must be equal to 3/4 because the dimension must be the same as the dimension of SLE 8/3 paths, which is 4/3. These have dimension 4/3. Therefore, nu must be what gives dimension 4/3. Therefore, nu is equal to 3/4. I had an A and a B, which were functions of nu, gamma, and rho. Nu is 3/4. I have A and B. I now know the values of A and B. I can compute gamma and rho. And for instance, I can compute now the gamma must be 43/32. But I think I'm out of time, so I think I'll stop there.
Your third assumption had two parts, one of which was this very natural condition that almost sounded obvious, and the other one was saying that this is in fact one of the SLE kappa.
That last assumption probably is not needed. I'm 98% sure. But it was however, historically, it was the right assumption to look at as to why SLE should be the limit. And that's a key, why should you expect an SLE to come out of this? It's because of that property. It's not really an assumption.
If it's true that you define correctly Markov process, what's the generator?
It's not a Markov process, except on path space, in which case the generator is hard to describe. In which case, I can't do a generator on path space right now. It's not a Markov process on space. It's only on path space.
So you showed that the self-avoiding walk is very special as percolation. Is there anything such special property of the boundary of percolation cluster, the one with exponent 7/4?
Yes, that's the the locality property of SLE 6, which I didn't describe in this, is relevant in I mean, in determining that's SLE 6 and getting the boundary of 7/4.
Locality of that's locality of the interior.
Locality of the curve that Oded did that goes along, that sort of curve, which is what is dimension 7/4. That curve that Oded drove in a percolation cluster doesn't feel the boundary. And that's the locality property. There, vaguely.
For non-intersecting curves, is locality equivalent to restriction?
No, the self-avoiding, the 8/3 does not. If you think about the self-avoiding walk thing, the infinite self-avoiding walk condition that you start and get someplace, once you've gone the whole distance, it satisfies restriction. But if you only see a little piece of it, it doesn't satisfy it, and that's the difference.